And now, a short series of videos about what is almost certainly the fundamental problem in analog electronics: circuit analysis. First of all, I need to define what I mean by circuit analysis. The problem of circuit analysis is to work out any parameter of a circuit, by which I mean the voltage at any point or the current through any component, given details of the components in that circuit. So if you're given a circuit diagram with a set of resistors, diodes, current and voltage sources in it, the problem is to work out what the currents and voltages are throughout that circuit. One point to be aware of before we start is what I mean by voltage. As we've seen in the talks about electric and magnetic fields, the voltage is associated with the electric potential, and every point in space has an electric potential associated with it. However, as we've also seen, the only place where you can be sure that the electric potential is zero is an infinite distance away from all charges. You can be absolutely confident that any circuit that we're going to build in the labs is not an infinite distance away from all charges. And therefore, we cannot use that as our zero of voltage. So, we just pick one. The choice is not quite arbitrary, although it could be. We are free to pick any point we like in our circuit and define it as being 0 volts. Because everything that we've been doing is a function of the difference in potential, or the difference in voltage between 2 points, and not the absolute potential at any point. Ohm's law is about the difference in voltages across a resistor. A voltage source ensures that the difference between the voltages on its two sides has a certain value. Kirchhoff's voltage law is all about the sum of the voltage changes as you move across components in a circuit. None of these laws tell us anything about the absolute value of the voltage at any point in the circuit, because it doesn't really matter. Sometimes we call the 0 volt point in our circuit ground. And sometimes it literally is ground, in the sense that you take a big metal stick and you hammer it into the ground, and the potential of that stick, that is our local 0 volt reference. Other times, when you have a battery-powered circuit, for example, not connected to a big stick going into the ground, we usually pick the negative terminal of the battery, and we define that as being our local 0 volts. But in all cases, the choice is not that important. We are free to pick any point in our circuit we like, and just define it as being our local reference, our local 0 of volts, and then measure all of our voltage differences relative to that 0 volts. That's probably the most confusing point about circuit analysis, so I wanted to get that clear before we start. Now, we've already been doing circuit analysis in the sense of working out what the voltages and currents are given a circuit. I'll just recap a couple of simple cases. This one. What current flows in the resistor? Well, it's just Ohm's law. We know that the function of this voltage source here is to raise the potential at X 10 volts above the potential at the negative side of the voltage source. We've defined the negative side of our voltage source here as being our local 0 volts. We know that because we've connected it to this ground symbol here, which is telling us that this is our local reference of 0 volts. So X is 10 volts above 0 volts, so X is at 10 volts. The other side of the resistor is connected to 0 volts, so we have 10 volts across our resistor. We can then just apply Ohm's law. The change in voltage across the resistor is the current through the resistor times the value of the resistance. 10 equals I times 2K, and therefore I is 5 milliamps. That's it. We have done a bit of circuit analysis. we have worked out the voltages and the currents at all points in the circuit. A slightly more complicated one, which should also look very familiar. This circuit. What is the voltage at node X? Well, it's everybody's favourite circuit. It's a potential divider. And we've seen lots of these before, and we'll be seeing a whole load more of them in the remainder of this module. We can just apply the potential divider formula and determine that X is 10 volts times 3K divided by 5K, which in this case would give us 6 volts. If we wanted to work out the currents in this circuit, we could just combine these two resistors in series, determine that together they behave like a 5K resistor. You just add up the resistances of two resistors in series. We have 10 volts across this 5K resistor because this point would be 10 volts above 0 and this point would be 0. So we've got 10 volts across a 5K resistor. So the current flowing through both of these resistors and the current flowing through this voltage source would just be 2 milliamps. We now know the currents through every component in this circuit and the voltages at every point in this circuit. We have solved this circuit. These were two very simple examples. In the general case, we have to use some other techniques. If the circuit is linear, we can use superposition, and that simplifies the analysis greatly. But there are some other techniques we can use as well. The use of equivalent networks can help, and in particular, a technique called source transformation. And we'll talk more about both of those in subsequent videos. I should also mention that in the general case, where we can't use any of these shortcuts, there are two algorithms which will get you to the answer. These are called nodal analysis and mesh analysis. I'm only going to talk about nodal analysis because it's easier. I can't think of any reason to talk about both methods because they both get you to the same point, so we might as well take the easier route. And that's nodal analysis. And I'll be describing that algorithm in a subsequent video. Nodal analysis is how almost all simulation programs work. It's how they solve circuits. In the next video, we'll just be revising the fundamental equations that underpin all of these analysis techniques.